Hi everyone, and welcome back to another deep dive on Metasploit Encoders. In this episode, we'll look at the Alphanumeric Mixedcase Encoder. This encoder is special because it generates payloads with instructions containing only alphanumeric characters, lowercase and uppercase. Having a payload made up only of alphanumeric characters can be really useful, especially when exploiting buffer overflows or other vulnerabilities in applications that apply input filtering. I have a mini cheat sheet here with all the MSFVenom commands, and first I'll generate the shellcode C array. We can also generate the shellcode in raw format to quickly have a look at its assembly instructions or convince ourselves that it's only ASCII. See here, with the exception of the first few instructions, everything else can be represented only using alphanumeric characters. Very nice. We'll take care of these first characters later. For the moment, let's also generate an executable and test it to check if the shellcode works automatically using MSFVenom. I'll then copy the executable to a Windows 8 VM for testing, where I also have a wrapper C code for the shellcode, as we've seen in other videos. The executable generated by Metasploit should work as expected and produce a message box. Then I have just the shellcode array added to the wrapper code. We'll see in a minute why this is useful. The rest of the code in the wrapper is the same as we've seen in other videos, so I won't go into details. We can quickly compile it using CL command line tool. Okay, this is the compiled wrapper. It works as well, same result. Let's see now how to get rid of those extra non-ASCII characters in the beginning of the payload. There is actually a helpful mention in the Ruby source code for this encoder. Let's check. Locate the source code. Open it with your preferred text editor. Most encoders allow us to specify extra options which are read from the data store. So that's a quick way to find out which options are supported for this one. Although not specifically documented, this encoder accepts two options, a buffer register and a buffer offset as parameters. Let's check out the source code. The description mentions that a pure alphanumeric shellcode is not possible without a register to point at the shellcode. This is because of the getPC instructions at the beginning needed to get its address in memory. Interesting. The shellcode address is obtained using the fnstEnv instruction, which gets the FPU environment and stores it on the stack. For more info about how this trick works, check out the video on the Optimised stub encoder. Although these instructions cannot be represented using only alphanumeric characters, there is a workaround. We will use a register and manually point it to our shellcode exactly as we've done in the video on the Optimised stub encoder. I'll use EBX in this case as the buffer register, same as in the other video. Then generate the shellcode again in raw format to observe the difference. we should see that we get rid of the initial non-alphanumeric characters and the payload looks nice and clean. We now rely on EBX to point to the shellcode instead of using the FSTenv trick. We next need a bit of manual assembly in order to point EBX to our shellcode. We can do that easily using inline assembly. Let's go back to the C wrapper code and see how to do this. But this is a simple example and we can embed the shellcode as we like into our wrapper application. What about a real-life exploitation? How would this trick work? We usually end up with a register pointing closely or even right at the shellcode, and we would use that as the buffer register parameter. Check the simple modification of the code. Before converting the shellcode to a function pointer and executing it, EBX is set to point to its address in memory. EBX will be used inside the encoder as the base address. Also, notice an added benefit of having an alphanumeric shellcode. We can actually just type it here, a few lines of characters, instead of specifying a large block of hex bytes, as we've done in the previous videos. Looks nicer, right? Let's compile the second version of the wrapper and see how it looks in a disassembler. I'll open it in IDA Pro. Cross-reference the offset of the shellcode to quickly go to the code where it's used. It's used in a call instruction. Set up a breakpoint and let's debug this and see what's happening. Why does it work? First thing to notice is that all these instructions here are represented by alphanumeric characters. If we set the number of opcode bytes, we can see based on their values that the hex bytes correlate with ASCII characters. If you want to go manually through this code, you'll notice that it's actually pretty long because it's a bit more complicated to create shellcode containing only alphanumeric characters. Just stepping through, we'll reach the decoding routine and we can see how the following bytes get decoded on the fly to create the next stage. Nice! You can see how the message box shellcode is being built with bytes decoded one by one using a simple XOR decryption routine. Also, set a breakpoint on the beginning of the next stage so we don't accidentally go past it. Or we can simply press F9 and let it run until it decodes the next stage completely. Real-life applications have limitations on the input characters they accept, so being able to generate a full ASCII shellcode is quite handy. ASCII characters are usually accepted and go past any filter. Going back to the encoder source code, we can get more information about the way it works and the parameters. I encourage you to take some time and understand it. Maybe you want to create your own encoder and have the shellcode only use a specific character set. Have fun! I hope you found this encoder-decoder interesting and you'll use it in your further exploits. If you're curious, there are other interesting ones as well to play with. If you haven't already, check out the video on the Optimised sub-encoder. That one has some similarities, but also an interesting twist. After watching this, download the code and practice on your own. Thank you very much for watching and stay tuned for the next deep dives. Cheers!